Okay, howdy. So this is lecture 10. We're talking about forces from fields now. We're going to talk about three different things that feel forces from fields. The first will be an electron, or a charged particle. A charged particle will feel a force based on how it's moving. Okay, so a charged particle that is not moving does not feel a force from a magnetic field. However, a charged particle which is moving with respect to the magnetic field does feel a force from the magnetic field. Next, you have the current. The current in a wire will also do that. That'll actually be third, I guess. But the current in the wire, which is basically a bunch of moving electrons, will also create a force, or feel a force from a magnetic field. And then finally, we'll talk about the magnetic moment, which is really the basic source of magnetism, at least from an electron's point of view, and from a permanent magnet's point of view. And that will be a little bit more complicated. That will be the next thing after this. That's going to be just like the dipole moment of the electric dipole moment. It'll have a very complicated relationship with everything we do. But what we're going to start with is just a particle moving along a path like this with a velocity v. That's going to be perpendicular to, well, it's going to have an angle with respect to the magnetic field. So we'll put that angle in there. Okay, so that's b. And so then there's going to be an angle theta between the path of the particle and the magnetic field. Actually, it's the instantaneous velocity of the particle, because what will happen is this is going to create a force, and then this particle is going to start turning. Actually, we'll talk about that in lecture 12, exactly what the motion is going to look like in this field. Right now we just want to talk about what the force is, so we can do things like magnetostatic calculations or static calculations. So we'll talk about things that are viable with Newton's first law here. We'll talk about dynamics, Newton's second law, in lecture 12. So what happens here? Well, this is going to feel a force, and that force, it's a good color, will be perpendicular to both of these, so it'll be coming out this way. So it's perpendicular to both of them. Perpendicular to both the magnetic field and the velocity of the charged particle. Let's say it's got a charge q. All right. So that's what's happening here, is that this is going at some weird angle. Now, I did give you a video somewhere to watch to talk a little bit about what's going on here, so you understand why this is, as far as relativistically. But this is basically what you see happening to a particle like this. So this is 2. Electric charges feel a force. Okay, it's supposed to be 2 words. From magnetic fields it's going to be based on that. It's actually going to be proportional to their speed. This is technically their speed relative to the magnetic field. You don't have to worry about that part. So your magnetic force in this case is going to be the charge. So a particle with a larger charge will feel more force. A particle with a negative charge will have a force going out the opposite direction here. So this is for negative charge. Also proportional to b, also proportional to the velocity, and I do that in the opposite order that you're supposed to, and times the sine of that theta. So in this case, if you're moving parallel to the magnetic field, you don't feel any force. If you're moving perpendicular to it, you feel the maximum magnetic force. All right. So going along the force does not accelerate your charged particle. All right. Going along the field, going along your magnetic field does not accelerate it, which is the opposite of the electric field. Right. The electric field would pull that thing along its direction. In this case, it pushes it to the side. So the electric field sort of accelerates the thing along that direction. The magnetic field turns it in that direction. All right, so that's sort of the dynamics, and that's what we'll talk about in that was one in lecture 12. Okay, let's see. Oh, we need to figure out the direction. So you see there are directions here, and we need to figure out that direction. So we're going to have to do another right-hand rule, right? And we'll do right-hand rule 2, which is going to say that if your index finger points in the direction of the velocity, and your, what is that other guy? Middle finger points in the direction of the field, then your thumb, which you stick out perpendicularly to your hand, to your fingers, is going to go in the direction of your force. Okay, so that is, if you go this way, right, with your right-hand rule, so that's your velocity, that's your, actually, you're reversed, so ends up going like velocity, field, force, okay? It's hard to remember what's reversed and what's not, so let's see. So I'm going to pretend it looks like this. All right, so that's your force coming up this way, your field that way, and your velocity that way, and hopefully that looks like a right hand and not a left hand. Right, should be with a right hand. I think this is right. Okay, so that's how you get the direction. Now remember, if this is a negative charge, it goes in the opposite direction. Okay, so just keep that in mind. All right. So positive charges, you use the right-hand rule. Negative charges, you do the opposite. I could actually use the left-hand rule, but we're not going to do that. We're just going to say go in the opposite direction. All right. So we're not going to try to use different hands for different charges because it's bad enough already. Students have a hard enough time with these things already, figuring out these directions. Because it's kind of weird, because you push this way with something that's going this way and it comes out in the other direction, right? So we just need a way to figure out which direction is which, all right? So hopefully that all looks beautiful to you. It looks wonderful to me, and I will talk to you next time about magnetic moments and all the weirdness there, all right? Bye now.